Good morning, all of you. At the very outset, I would like to thank the organizers of this symposium, particularly Dr. King, Director, Hydrogen Research Center, and Dr. Sangsar Hung from Kiev, who have made it possible for me to be amongst you this morning to share some of our experiences in the area of hydrogen storage. The outline of my presentation is, after a brief introduction on hydrogen and the hydrogen storage, routes and limitations. I will also be briefly talking about the Indian research programs, that is the research programs related to hydrogen economy pursued in India, followed by hydrogen adsorption, challenges, adsorbent materials, and the desired characteristics, microporous and mesoporous adsorbents we have been pursuing, and evaluation of hydrogen onboard storage system. We have undertaken evaluation of metal hydride based storage system on a three-wheeler in IC engine, that is internal combustion engine, not through fuel cell. I will be sharing some of those results as well. Hydrogen, as you are aware, is an energy carrier and has got several advantages. Can be made from a variety of raw materials, including water splitting and fossil fuels. Has zero emissions at the point of use. However, depending on where you produce it or the starting material, if it is from fossil fuels, of course, there will be emissions. However, still, the overall well-to-wheel emissions in both air pollutants and greenhouse gases, the hydrogen it gives you very low emissions compared to the conventional fuels such as gasoline. Fuel cell technology, for which hydrogen is fuel, and this is the major driving force for hydrogen economy, is fast emerging as a mature technology, and so far the cost of fuel cells was a major impediment, but now I think the costs are really coming down, and this fuel cell technology is maturing very fast, and that is where the hydrogen is becoming more and more interesting and important. Then the another most important thing is hydrogen through fuel cells can achieve well-to-wheel efficiency of 22% compared to 12 to 13% for gasoline and CNG in IC engine, and 18% for diesel in internal combustion engine. That is, the overall efficiency from well to wheel, which is more important, is of course very high with hydrogen. Hydrogen as a fuel can be used both through fuel cells and in internal combustion engines as a direct fuel. When you use hydrogen as a direct fuel, there are advantages. The characteristics such as low quenching gap, high diffusion coefficient, and wider flammability, which result in completeness of combustion, hence higher efficiency, low burnability, leading to low NOx, and this is very important. I will come to this practicality later, how this can be used along with CNG to reduce emissions in IC engines. Safe even in case of leakages in open air because of fast diffusion. However, there are few problems when you use in IC engine, hydrogen in IC engine. High flame speed and low ignition energy are problems because they can lead to pre-ignition and backfire, which can be dangerous, and is unsafe if there is a leak in a closed space, like within a vehicle when it is closed. The barriers to hydrogen economy, there are many, as you are all familiar, but onboard hydrogen today is probably one of the most important barriers which has to be overcome, which is topic of today's presentation. Hydrogen storage limitations and challenges, probably you would all be aware, so I may not spend much time on this. I quickly go through. Weight and volume are the major problems. The hydrogen storage systems occupy huge volume and are very heavy. Efficiency is a major again challenge when you are looking at the storage systems. Whatever system you look at, whether it is compression, liquefaction, or storage in solid materials, you have to spend certain amount of energy either to compress, liquefy, or to take out hydrogen from the storage materials using some of its efficiency. Durability, those who are dealing with hydrogen storage systems on board would realize that it is not important, it's not only important to have high capacity when you work in the laboratory or when the system is very fresh, but it has to sustain that capacity over a period of time, several cycles, and the ideal lifetime is 1500 cycles. Refueling time, of course, it has to be fast enough. Cost is another major factor. As developments takes place, I am sure the cost will come down. And of course, as the case with any other fuel and systems, codes and standards, they all will emerge. And of course, life cycle time and efficiency analysis has this also in-depth study is required. Hydrogen storage targets, you are all familiar. Earlier speaker also talked about. I would just like to draw your attention here only to these targets. One is that 6% weight percent by 2010 and 9%. Of course, the earlier speaker shown your targets as 6% by 2010. In India, there are a number of research programs undertaken related to hydrogen economy. One of the important programs is National Hydrogen Energy Board program of Department of Non-Conventional Energy, Government of India. It is a 10-year program, and the budget that is expected to be spent is about equivalent to $70 million. Ministry of Petroleum and Natural Gas, Government of India, has a program for 5 years and expected to spend about 20 million. This is mainly oil industry, refineries. Then there is a CSIR, Council of Scientific and Industrial Research. The research initiatives there cover production, mainly autothermal, storage, there's carbon-based storage materials they are working, and of course fuel cells. The other initiatives are initiatives of core group on automotive research, REVA program, a private initiative. It's a private company in India who are producing electric vehicles running on batteries which are recharged from grid power. They are now working on fuel cell based hybrid vehicles. And Benares Hindu University, they have been working for a very long time on metal hydride storage. The National Hydrogen Energy Board programs, they have 3 types of programs: short term, medium term and long term. Under short term, use of 10% and 30% hydrogen in admixture with CNG in buses and small and large three-wheelers. This program is for about 2 years. In India, CNG is picking up very fast, and in New Delhi, there are about more than 10,000 buses. All public transport runs on CNG. Taxis, three-wheelers, and buses. And this is now extended to other cities. CNG has brought in, when we have switched over from gasoline and diesel fuel to CNG, it has definitely brought down the pollution with respect to particulate matter, SOx emissions, CO and things like that. But NOx is a problem there. CNG, in fact, there are studies which show, contradictory studies of course, show that even NOx have gone up, NOx emissions have increased, some studies show. When you use hydrogen, mix hydrogen with CNG, 10 to 30%, some studies showed that there is considerable reduction in NOx emissions. Hence, it makes sense and it is relevant. It's called hethane in some places. So these studies are undertaken where it is used in IC engines. And in the midterm, they have a program on again developing IC engine, it is internal combustion engine with 100% hydrogen, three-wheelers, buses and things like that. And of course the storage material mainly metal hydride. It is perceived in India that fuel cell based technologies would be cost prohibitive, and it may be at least in the short term it may not be feasible for us to get in a full way. So it was probably felt that if we have go for IC engine based hydrogen economy, maybe we would gain considerable experience in other systems like transportation, production, and its use, safety, all those issues we can gain experience. As and when the fuel cell costs come down, maybe we can enter into fuel cells. That is one strategy which probably we are pursuing in India. Long term, of course, bus and three-wheeler. Three-wheeler you see everywhere is would be coming because the population of three-wheelers are pretty high in India. Initially, of course, this acquired fuel cell and later on indigenous development. These are the programs. And the next important program is by Ministry of Petroleum and Natural Gas. Here the focus is on production, storage and distribution, and of course the application-oriented research in IC engine three-wheelers and examining economics of use of metal hydrides and fuel cells from a long-term perspective. These are some of the programs which Petroleum Ministry, mainly the oil companies, I come from Indian Bharat Petroleum Corporation Limited, the refining and marketing company. We are also working in these areas. The other program is auto industry, the Society for Indian Auto Manufacturers. They have a program to develop hydrogen IC engine and demonstrate a fleet of about 1,000 vehicles by 2008 and 200 buses, 500 small three-wheelers and about 300 big three-wheelers. At Bharat Petroleum, where I am working, our corporate R&D center has undertaken research programs on development of materials for hydrogen storage, adsorbents, that is based on physical adsorption, mainly microporous and mesoporous materials, and complex hydrides, metal hydrides and complex hydrides. A pilot study using a three-wheeler on board the compressed hydrogen in cylinders and metal hydride canisters. I am going to share some of our results on this. Hydrogen storage materials, maybe you are familiar with this. with lack of time, I would skip this slide. The materials based on physics option, some of the materials which we have evaluated or synthesized and evaluated are activated carbons, mesoporous and microporous materials, and of course metal hydrides and complex metal hydrides. I am not going to give much on complex hydrides because it is very recent work. When we look at, we want to have an adsorbent based on physics option, it is very important to look at the properties of hydrogen. If you look at hydrogen, I would like to draw your attention to this property, that is polarizability, which is pretty low. Even argon has got, which is inert gas, has got double this value, has no quadrupolar dipole moments, and hence the hydrogen can have, if there is no chemisorption, if there is no reaction, then you can have very, very weak interaction, and hence the only way you can have large adsorption or higher adsorption capacity is to have large surface area or very high pressure. The number of new generation materials are there which are coming up and which are being investigated. I would like to skip this because earlier speakers and speakers later on are also going to cover a lot of these aspects. It will be more of repetition. But with respect to physics option or physical adsorption based materials, I would like to show this slide. This is from literature. The reference is given here. If you see, among all these materials, activated carbons are showing high capacity, and this particular norid carbon shows the highest so far reported. And here the ZSM5, that is another material which is showing higher among these materials, though as such these capacities are pretty low. What it shows is that only those materials where the surface area is high, you have higher capacities. Here the surface area would be of the order of 3000 plus. In our laboratory, we will try to look at some of the new microporous and mesoporous materials which show some promise in hydrogen adsorption capacity. Particularly these nickel-based phosphates are interesting because, or at least we thought are interesting because these have got unsaturated nickel 2 plus in the framework, which can have specific interaction with the hydrogen, and hence we synthesized VSB5, which is thermally stable 24-membered ring microporous framework with a pore diameter of about 1 nanometer, having hexagonal symmetry structure, and nickel to phosphate framework ratio can be varied. Actually, we synthesized in this range. Surprisingly, these materials did not show good capacity. The maximum that we could get is 0.35, which is pretty low. Then the other materials which we have looked at are aluminophosphates. In particularly, I would like to draw your attention to the SSZ series. These are very new materials which are reported in the literature. We have worked on SSZ51, and this material showed about 1.1 weight%, which is the highest compared to any other inorganic porous materials which are reported in the literature. And these are preliminary results. Now we got, which I am not able to share with you. We need to repeat some of those results. We are getting, we optimize the synthesis conditions, and we are getting far better results here. Other materials, MCM 41, SBA 15 did not show much capacities. Activated carbon, some materials we evaluated and they are comparable to what is reported in the literature. This is the comparison of various materials which we have evaluated in our laboratory or synthesized. And of course, this is taken from the literature, the DSM-5. The SSZ here compares favorably with other inorganic materials. And SSZ series 54 is another material which is showing even better performance than SSZ 51, which I could not include here. To summarize whatever has been presented so far, a reversible hydrogen uptake at minus 196 degrees centigrade. Of course, this has to be taken to room temperature. Once it is easier to measure as at minus 77 K, and then after screening and having better material, then moving to room temperature will be easier. So that is how most of the people do. Aluminophosphate compositions have shown about 1.1 or more than that, and activated carbons about 2.8%. The minimum hydrogen uptake is observed for the mesoporous silica-based. Other materials they did not show, they are very low. To have better insight on specific adsorption sites and their optimization, better synthesis strategy are required to improve uptake capacity. Here, we need to do some simulations before even undertaking the synthesis. This is what we are going to do. Otherwise, we are unlikely to have better materials. I have a few more slides where I am going to present the performance of onboard metal hydride storage canister system which we have evaluated in a three-wheeler. Metal hydrides, we have two programs. One is on metal hydride evaluation, having about 1 to 2% hydrogen capacity, and complex metal hydrides, we are working on this particular system, lithium amide, which has shown a promise. Of course, there are issues with respect to reversibility, which we are trying to do, doping some dopants which act as catalysts to improve the sorption kinetics, particularly the desorption kinetics. Coming to the onboard storage system evaluation, this is a three-wheeler, a very popular vehicle. It's a passenger three-wheeler and three-seater vehicle. It is a four-stroke air-cooled CNG. It can run on CNG or petrol, both fuels it can take. And this engine we have converted to use hydrogen in place of CNG. The CNG power is 4.4 kilowatt at 5,500 RPM. Gasoline, when you use, the power is high. Fuel tank capacity, CNG is cylinder, 29 liter water capacity, and it can store about 4.6 kg of CNG at 200 bar, and gasoline 3 liter capacity. Hydrogen, same capacity cylinder as CNG, but it can only store, we have gone up to 150 bar, and at that pressure it can store about 0.35 kg at room temperature. This is metal hydride canister, which is, this is the one, this limit, which is fitted here. The space here is not enough, so it is protruding outside. There are 10 metal hydride canisters. This is one canister, so 5 in one row and 5 beneath. They are kept in 3 to 2 rows, one over the other, 5 in each row. And the capacity of this cylinder is 1.38 liters water capacity, and the weight is about 6 kg each cylinder, and the entire weight of the canister with other associated fittings and all is about 83 kg, and this is a nickel lanthanum mish metal material. It has a design capacity of about 0.7 kg hydrogen storage, and it can operating pressure is 35 bar. It can reach 45 degrees while charging, like when you load hydrogen to the system, the temperature goes up. So you have to have a cooling mechanism while loading or absorbing hydrogen. And in use, when you are drawing hydrogen, it can temperature can go down to -5 degrees centigrade. Hence, the startup is little difficult, because exhaust gas here, the exhaust gas is recycled. There is a facility here to recycle either cold fluid or the exhaust gases, so that the temperature can be moderated, like you either cool it or heat it. Otherwise, the kinetics are pretty slow. You do not recycle the exhaust gas, you just cannot run the vehicle, because enough hydrogen is not supplied to the engine. The preliminary results from this study show that fuel consumption is very low with hydrogen. It gave about per kg of hydrogen 140 kilometers, and when you equate with gasoline equivalent, which is about 38, compared to CNG 26 and gasoline 25, the fuel economy with respect to hydrogen, hydrogen compared to CNG is almost 1.5 times. However, the acceleration is pretty slow. Maximum speed that we could attain is just 35 kilometers per hour, compared to 60 for CNG and 65 for gasoline. And time taken to cover 1 kilometer is 175 seconds, 124 and 105. These are the comparisons, and the change in acceleration compared to CNG is almost 41% lower with hydrogen. The observations, further observations are, three-wheeler was run with onboard hydrogen canister. We have run about 1,000 kilometers on an average. Each filling cycle gave about 60 kilometer drive. Metal hydride storage, though designed for 1.2 weight percent hydrogen capacity on board, the system could only store about 0.85 weight percent. And this, over a period of time, can further go down. This is what I was telling. It is not only important to have a system which may work in the laboratory with high capacity, but when you go to the field, that is where it has to sustain. Otherwise, you will still have a problem. Metal hydride storage system is cumbersome compared to high pressure cylinder. With respect to the present system, these are, please do not generalize. There are few things which are specific to this particular system, and these results are specific to only this three-wheeler which we have evaluated. So I do not want you to extrapolate and generalize to other systems. Metal hydride storage system is cumbersome compared to high pressure cylinder, because the capacity is very low and it is very bulky, like 83 kgs is the entire system weight. That itself is pretty large. Additional load on the unit. And cold start is the problem with hydrogen canister when exhaust gas temperatures are very low. So you have to have a mechanism there. Hydrogen operation is, so what we were doing is we start with other fuel and then switch over to hydrogen when you have enough temperature in the exhaust system. Hydrogen operation is more fuel efficient than CNG or gasoline, about 50% higher efficiency, which we have seen in this. However, acceleration on hydrogen is inferior compared to gasoline because of power loss. Power loss is due to poor volumetric efficiency. About 30% of the cylinder volume as compared to 2 to 4% occupied by gasoline. So what it is because of volumetric density of hydrogen is pretty low. So engine itself has to be designed to have higher compression so that hydrogen occupies less volume and you can have more of oxygen in the system. Otherwise, the cylinder, most of the volume is occupied by fuel itself. So that way, power is pretty low here. So this is what our engine experts have concluded. To minimize power loss on hydrogen engine, modifications for higher compression ratio, retarded spark advance, timed gas fuel injection. These are the modifications our people have concluded and are about to do. These changes are planned. In conclusion, onboard storage is one of the major barriers for hydrogen economy. In the long term, solutions are expected from sorption-based storage systems. I am very sure that though as of now we are far away from the real targets, but the type of research that is happening and the type of initial results that are being reported, I am very sure that we will have solution in near future for the hydrogen storage in the form of novel materials. Presently known materials does not meet storage requirements. New materials based on both physical and chemical adsorption need to be developed, which is happening everywhere in the world. India has undertaken a number of initiatives to meet challenge of hydrogen economy. In the short term, India is focusing on CNG hydrogen admixture to get first-hand experience in handling hydrogen, which includes production, transportation, refueling, safety, etc. In the long term, development of fuel cell, new materials for onboard hydrogen storage, vehicles, technology, etc. are also parallelly being taken up. With this, I have come to the end of my presentation. I would like to acknowledge the management for permitting me to share some of these results, and also my colleagues who have helped me in preparing this presentation, and to the organizers and all of you for your patient hearing. Thank you.